Welcome to homework.
Alright, so in this question, we have to show that each of the graphs in the previous question has no cut edges. Now, in the previous question, we were given four types of graphs. Those are some special graphs. They're also mentioned in the section 10.2 of the book. The first one was CN. CN is a cycle graph or a cyclic graph that has an edge between every adjacent pair of vertices. As mentioned here, this is Cn for n equals 5. So we have to show that this graph, that is Cn, has no cut edge where n is greater than equal to 3. Now, if you take any cyclic graph, say with n vertices, it will have some edges like this and some vertices like this. Say this is a certain portion of a graph. Here are some vertices and edges, and here too. Now, if you cut one of these edges, say I cut this one, the graph you're left with is, say this was vertex v1, this was vertex v2, v1's here, v2's here, and the rest of the graph remains unchanged. What do you observe? You see that the graph does not disconnect. Basically, removing an edge from the cycle leaves a path. Although it's not a cycle anymore, but it's still a path that is not disconnected. Hence, we can say that there is no cut vertex for this graph. Cut edge. Alright, I hope that makes sense. Basically what we're doing is, if you still don't get, we're just proving that the removal of any edge from all these graphs will not disconnect the graph. So that's all we have to prove. Let me just write it down. We have to prove that the removal of an edge, that would be our cut edge, will not disconnect the graph. That is, make it into two disconnected components, as we saw in the first one, C of n, like cutting the single edge between v1 and v2 just left us with a open path, but the graph did not get disconnected. Yeah, so I hope that makes sense. Now let us move to part B, wherein we are given Wn. Now what is Wn? Wn is a wheel graph wherein we have certain number of vertices, and there is a central vertex from which edges emanate, and they are connected to all the other vertices of the graph. So these edges can also be called as spokes of a wheel, or viewed as spokes of a wheel. Yeah, so we are given Wn for n greater than equal to 3. Let's say we have a simple Wn for any arbitrary number of vertices. Alright, so here are some more vertices, some more edges. This is the center, and these are the spokes or edges. Now, mind you that all the vertices of this graph would be connected to the center. That's what we talked about just now. Now if we remove an edge from the, let's say firstly the cyclic portion of this graph, that is this one, we're still left with the connected graph, right? See, this was vertex v1 and v2. What we're left with is v1, v2, and the rest of the graph is just unchanged. Make sense? So there would be no cut edge in this case. We have one more case here. Suppose that we cut or we take this spoke as the cut edge. What would happen then? If you take a closer look, the graph would still be connected. We just cut this edge, but since it was connected through the cyclic path of this graph, the graph still remains connected. And so we have also shown for this part that there is no cut edge. Alright, next up we have another special type of graph, that is KMN. Now what does this mean? This is the complete bipartite graph, wherein the first one, that is M, and the second digit, that is N, represent the number of vertices on different levels of the graph. See, M equals 2, so here we can see 2 different vertices, and N equals 3, so here we can see 3 different vertices, and all these vertices are connected. Let's say this is a different set and this is a different set, so these elements of the set of this set are connected to elements of the other set, but they're not interconnected. So that's what a bipartite graph is. We're given KMN, where M and N are both greater than or equal to 2, and we just have to show that there is no cut edge for this one. What we can show here is that, let's say we have K of 2, 2, alright, and there are 2 vertices in the first set and 2 vertices in the second set. And let's say they are connected like this. Alright, now if you were to remove any edge from here, the graph would still be connected. And why is that? Because if you see, from V to X there's a path, from X to U there's a path, and from U to Y there is a path. Therefore there is a path from V to Y. Even though we just cut the direct edge from V to Y, there is a remaining indirect edge from V to Y. Therefore in general case 2, there would be no cut edge, as the graph does not get disconnected after cutting an edge. There always remains a connection, and that's all we have to prove. And the last part, I think we're given a n cube graph, yeah, for Qn, n greater than or equal to 2. What does an n cube graph mean? For any value of n, we just take all the binary numbers up to it and represent them as the vertices of a graph. So for n equals 2, you'll get 4 binary numbers from 0 to 2 that are 0, 1, and this is 3, this is 3, and this is 2. So for n equals 2, you get 4 different numbers, binary numbers, that is the length of the number is 2. For n equals 3, you'll get 8 such numbers. Yeah, so this can be thought of as 2 to raise to the power n different vertices. Makes sense, right? So let's prove for this one too that there exists no cut edge. So if you observe any n cube graph, what you'll see is that Qn would be just a connection of two copies of Qn minus 1. Now why am I saying that? Let's have a look. If you have Q3, that would be a cube with 8 vertices, because 2 raised to power 3 is 8, and you'll have 8 different binary numbers representing each of the vertices. So you'll have 8 different vertices. How can you arrive at this cube? You can have 2 copies of Q2, that are 2 squares, and you can just connect them with 4 edges, right? This makes sense. Now, without the loss of generality, we can assume that any of the removed edges is one of the edges joining corresponding vertices. That is simply, if there are 2 vertices, let's suppose that this is the cut edge. Alright, now each of these 2 components that are Qn minus 1s are connected by the remaining edges. Which edges am I talking about? This one, this one, this one. So no matter what edge you cut, there will always remain another edges, so that this graph does not become disconnected. Yeah, so that's all we had to prove. Therefore there is no cut edge for this graph. Get the point, right? No matter what edge you choose and decide to cut it, there will always remain some other edges through which the graph remains connected. So what we were to prove was that the graph does not get disconnected after removal of any edge, and we've proved that for all the 4 cases, and I hope that's clear. Thank you.